have done all kinds of design exercises to the game and changed incentives and information, whatever. But now they're standing in front of the agents who are going to play a game, and the question is, what can you get the agents to do? Now, if you look at like standard mechanism design since Meyerson, a little bit before there was some discussions of it, but I think Meyerson is where it really starts. That approach says, well, you're going to implement your best Nash equilibrium. And the idea is that you have control of all channels of communication, maybe in this world, but more generally, you think of your principal as being able to say, here's a Nash equilibrium, and because the principal is kind of big and central, and a Nash equilibrium self-enforcing, people are willing to implement it. They all think, well, everybody else is going to listen to you because you're big and central, so I might as well listen to you as well. So this is a case where the principal has full coordination power. You can really coordinate the agents on exactly what you want them to do. Then there's the other extreme, where the principal has no coordination power and can't even make sure that you can coordinate the agents on one single outcome. The only thing that you think the agents can do is the fact that they're rational and have combinability for rationality. And in those kind of, the smaller set of papers that takes this approach, but still non-negligible, you think of, well, any rationalizable outcome is possible, and I'm going to be conservative, so I'll kind of evaluate things going to the worst case rationalizable outcome. And so, in this case, you have no coordination power. Here you have full coordination power. We will propose a solution concept or an implementation concept, really, that bridges those two approaches.
מה זה agreeable?
Meaning they are not, agreeable will be ones who are willing to take the suggestion if it's self-enforcing, but that will become, define this much more precisely in a minute.
גדול זה, יש גם, שימוש כאן הכי גרוע, זה גם די מקובל, לא?
So right, so that is a difference, that's kind of something in between here. That is, you say they can coordinate, but I don't know on what they can coordinate, but that's assuming there is some coordination ability between them. But I think that still it's like, he's still thinking of the agents there as being able to do some sort of coordination. So I think that this, for us, this is the natural other end of like not being able to do any coordination with the agents. Okay. So like, how is our solution concept is going to work? Well, we're going to have, we're going to think of the principal as making some sort of suggestion before the game is played. This is not going to be an actual stage of the game, but we're going to kind of think of this as a fictional stage. And there are going to be some set of agents that are going to be agreeable who will follow, meaning that they'll follow the suggestion if it's self-enforcing. I'll define these things precisely in like 3 slides.
סליחה, הקצה השני היה rationalizability, זאת אומרת זה המינימום?
worst case, כן. הכי גרוע.
למה בעיניך זה המינימום, או למה אפשר להגיד שגם זה לא יהיה?
אז כן, אז אתה יכול, אם אתה רוצה, להגיד שאפילו הם לא, אין להם common belief of rationality, and which is fine. That's maybe not what we do, but I would say I think we usually think of the players as being kind of rational, and we usually make that at least that assumption in most of those implementation literature. But yes, you could. There are solution concepts out there. Like Phil has a paper that, and I think now Ehud Kalai and Adam Kalai have a string of papers kind of think about solution concepts where you don't even assume any kind of rationality in behalf of some of the other players. Maybe the best answer to what you're asking is that we're really trying to just relax the coordination part of what you can do, not the rationality and complex rationality part. In some sense.
אז זה הולך להיות כמו המאמרים של מרינה שעושים סדר מסוים על ה...
אז יהיה לנו אפליקציה אחת כזאת, מאמרים של מרינה, אולי מאמרים של אייל, ישראל בכל זאת, וגם כתבת מאמר אחד
וגם כתבו ביחד, כן?
כן. אנחנו קוראים לזה מודל הווינטר, אז...
אוקיי,
כן.
יפה, ריספקט.
אז כן, אבל... כן, אז יהיה לנו כזה אפליקציה כזאת, אבל זה לא רק כאלה. Good. So we'll have agreeable agents who will follow suggestion if it's self-enforcing. So you're going to make a suggestion. After that, if it's self-enforcing and the thing is way undefined, that will be the key thing, is the definition. Then they'll follow it. And then we'll have our principle is still going to be conservative. So they're going to evaluate things according to the worst case. But we will end up getting, with our definition, that if all your agents are agreeable, so if you're all willing to take your suggestion, if it's self-enforcing, then the thing you will end up getting as an outcome for you as a principle is the best Nash. And if nobody's agreeable, then you're going to get the worst case rationalizable. So in that sense, we'll kind of be bridging the two cases. And we'll have a general theorem about supermodular settings. So, perhaps the main setting that you're worried about multiple equilibria or multiple solution concepts is the cases where there's strategic complementarities. And so we have, and that's also the case where like rationalizability and Nash speak well to each other. And so we'll have a characterization of the best thing that the principle can implement in those kind of settings. And it will be the highest Nash equilibrium that has the form highest Nash among the agreeable players holding what the disagreeable players are doing, and the disagreeable players taking the lowest Nash equilibrium or the lowest rationalizable action, given what the agreeable players are doing. So there's going to be a bunch of those kind of Nash equilibria, and in some sense, the value of the principle is going to be the highest among those.
ה-agreeable משחקים נאש, הם כביכול יודעים מה כולם עושים.
Let me get there. Okay. I agree that this is a little, at the moment, this is very vague, and you're trying to guess what my definition is going to be. And perhaps I should have just started with the definition after that first slide. Sorry, I understand what you're asking, but let's wait with that, and you'll know what I'm talking about in I think 3 slides, maybe 4 if you include like a title slide or something. And then we have applications, network games, where we'll see that what you'd like is to have the agents, the agreeable agents dispersed all over the place. We'll also consider cases where agents don't exactly know who's agreeable and who's not, and so on. And there we'll see that often it's enough for me to think that you might be agreeable, even for me to think that you think that somebody else might be agreeable. So a higher order kind of agreeableness is going to be valuable. Then we'll have the winter application, so like team incentives, where we have some like rankings and so on. And we'll also talk about doing kind of mechanism design, more like screening style exercises. And then we'll have an application where all you want to do is get information from people, and we'll see how having agreeable people enables you to elicit information from the disagreeable. There's some related literature. Out of those, we're going to do stuff with rationalizability, so that's a Burnham and Pierce case. Our definition that relates to the agreeableness will borrow an idea from this tiny literature on something called preparation sets. So that's what this Vorneveld and Trasher-Vorneveld paper do. You don't really need to know what it is, but I'll just point out what that kind of means when I get there. There are solution concepts in the literature that bridge Nash equilibrium and rationalizability. That's the Rubinstein-Molitsky and the Miklavsky-Sadler. And there's also Elias and Kalai. They play around with a solution concept that bridges like dominant strategy and Nash. But these are, the thing that these things are missing compared to what we have is like the worst rationalizability and best Nash component. Because there, all it is a solution concept that gives you, a set that can go from the set, let's say, of rationalizable strategies to the set of Nash equilibria, why would you at some point switch from evaluating the set according to its worst case to its best case? You know, those things will not give you any guidance to that. And we will get it from the fact that the principle has the ability to coordinate agents. Then we'll do things with supermodulars, which relates to that literature, and there's the stuff related to applications. I don't want to talk too much. I mean, I have to answer questions about it, but I think it's not that super important. So let's get to the theory, the model, and the exact definitions, and then we can see exactly what they're meaning by this. So let's start with just having a game. Okay, so we're going to have a set of players I. Every player has a set of actions xi. It's going to be a characterizable space. Players' utilities are just some continuous function of those strategies. And we're going to have a principal who has an objective that depends on the strategy profile chosen by the agents. And that's the one thing we'll add to a standard game. We'll use SI bar to denote player I's set of mixed strategies. And most of the time, we won't be thinking about the pure strategies. We're thinking mostly about the mixed strategies. And to avoid having to write integrals of integrals and integrals of integrals and so on, we'll just do the usual thing where we extend our objectives to the domains of all distributions over strategy profiles and all distributions over strategy profiles and so on using expectations. So just kind of extend things linearly.
Objective זה של הקורדינטור?
Yes. Okay. The principal is the one who's going to try. Yeah. So we have every player has their own utility, UI, and then we also have pi for the principal. So before the players play the game, we're going to think of the principal as making a suggestion as to what to play. Now, what is a suggestion? Well, a suggestion is going to be a closed product set of mixed strategies. So every player is going to have their own kind of set of mixed strategies. Okay, so we'll have this like SIs, which you can think of as either as like a vector of sets or a product set. Okay, think of these interchangeably. And the idea here is that I'm going to say, Yuval, please play one of these strategies, Zivi, please play one of those strategies, and so on. Okay.
It can be a continuous range of values?
It can be, yeah, it's any closed set of mixed strategies too, so it can even, and the fact that we're making these as product set, it means that I cannot kind of I cannot make you two kind of take something at the same time. It's the idea I'm saying, look, I can tell you individually what to do, but I cannot tell you as a group, please play all this thing.
אני כשחקן דייר כהמלצה שלי או את כל הפרופיל שם?
אני יודע את כל הפרופיל. I know the character graph. Okay.
אבל זה רק נקודה כל המלצה?
No. כל המלצה זה קבוצה.
לא, לשחקן פרטי, לשחקן אחד.
זה עדיין קבוצה. עכשיו, למשל, כל האסטרטגיות הרציונליזציה, רציונליות.
אבל זה יכול להיות בפרט נקודה.
יכול להיות, כן. זה יכול להיות נקודה לכל אחד, ואז זה פשוט פרופיל.
כן.
אבל זה יכול להיות גם קבוצה לכל אחד. זה יכול להיות גם, אני פשוט אומר לך, דרך אחת להגיד, אני לא נותן שום המלצה, אז אני ממליץ לך את כל האסטרטגיות המעורבות שלך. That's about it.
אנחנו מניחים שאני לא יכול להגיד לשחקן, אמרת לשחקן השני משהו כזה?
כל השחקנים רואים מה אמרתי לכולם, ואני לא יכול, הדבר שאני מניח פה, the thing we're assuming is, שאני לא יכול לתת לך המלצות פרטיות. אז אני לא יכול להגיד לך, תעשה את זה, וכשאני אומר לך, אתה יודע, אתה לא יודע, אני מניח matching pennies, אומר לך play heads, זה נותן לך איזושהי אינפורמציה על מה מישהו אחר הולך לשחק. זה אני לא, כאילו, ההמלצות כרגע הן פומביות.
איך אינפורמציה? אתה יודע מה מישהו אחר? אתה הפרינסיפל, אתה יודע מה מישהו
לא,
אחר?
אני יודע מה ההמלצות שאני אומר לאחרים.
כן, אבל אמרת שזה public information באמת.
כן, זה public information, כן. זה מה שהתכוונתי, שזה הדבר שאני... זה ההנחה. וההנחה היא כאילו אין קורדינציה במובן הזה, שאני אומר לכם סטים, כולם יודעים את הקבוצות, אבל אני לא יכול להגיד לכם כאילו, אתם יודעים, שניכם תשחקו heads או שניכם תשחקו tails, אני יכול להגיד לך heads, tails. עכשיו זה רק suggestions, it's not what suggestions are implementable. So that's the key thing is what suggestions are going to be implementable. And in general, we're going to think of a suggestion being implementable if once you make the suggestion, you can be sure that the players will actually play in that set. Now, how on earth can you be sure that the players will play in that set? We're going to think of like, you know, this is coming from two things. We're going to have some set of players, where these are the agreeable players that I've kind of alluded to from before, who if you suggest to them something that we generally consider is rational for them to follow, they will be willing to follow the suggestion. Okay? And second, this is going to be general common belief of rationality. Okay? And of course, all players are going to be rational.
אז מה המשמעות של רציונליות בהקשר הזה? אני לא מניח שאחרים מקבלים את ההצעה.
So we're working on epistemic foundations. אנחנו עובדים על ההנחות הזה. Let me give you the exact definition, you can see it. Okay? And then hopefully you'll agree with me that this is sort of works. So we're going to have A being the set of agreeable players, and all the other players, those are going to call them in the set D. These are the disagreeable players. Let R be the set of correlated rationalizable strategies, and from now on, whenever I say rationalizable, I'm going to mean correlated rationalizable.
זה בסדר אם אני לא זוכר מה זה? כל המסגרה שלנו?
It is, there's, so if you do iterated deletion of strictly dominated strategies, that's like that, okay? It's a little different.
מארגן את הארוחה.
אם אתה כמו מוחק אסטרטגיות נשלטות, זה מה שישאר חזק.
זה מה שנשאר.
וה-correlated אומר שזה משהו שיכול להיות best reply, משהו correlated.
כן, בדיוק.
אז זה עובד הגדרה שקולה.
כן, אלה הגדרות שקולות, ביחס.
ומי יודע מי זה A ומי זה D? שחקנים יודעים?
כולם יודעים מי זה A ומי זה D.
גם מתכנן יודע?
גם מתכנן.
כולם יודעים בכמה knowledge.
כן.
מה אמרת ששקול rationalizability ו-correlated rationalizability?
No. correlated rationalizable.
כן.
ומה שמקבלים כשמוחקים אסטרטגיות נשלטות.
נשלטות כולל correlated.
לא. אם אתה עושה...
נשלטות, בלי קשר לשיווי משקל.
אם יש לך רק שני שחקנים, אז זה לא משנה correlated, לא correlated. אם יש לך יותר משני שחקנים, אז אם אתה מוחק אסטרטגיות מאסטרטגיות נשלטות, נכון? אז בסוף אתה מקבל משהו שהוא יותר גדול מכל הדברים שיכולים less response לאיזושהי מינה שאנשים מקבלים החלטות בלתי תלויות. צריך להגיד את זה בעברית. כן? like independent, right? So usually we think of rationalize, Pierce defined rationalizability with like independent beliefs, independent of each, that other players are independent.
Mm-hmm.
If you do that, then you don't, and you do iterated deletion, you get kind of a too large of a set. Because some things can only be justified as best replies to a correlated belief, belief that other people are correlated. But we're going to use the correlated version so that things can be justified using beliefs that involve correlation between the other players. Okay? So that's what that correlation means.
אז הוא מגדיל את זה.
כן. אבל...
זה R הזה זה ביחס להמלצה
strategies in the game. So you can think of a different kind of game where the players who are agreeable have to play according to their suggestion.
And must play independently.
Yes.
You don't, so
Yes.
do not allow correlation between the agreeable players.
So the right. So the game. Sorry, 1 second. The game there is the game they must play independently, but the set of rationalizable strategies is like with potential correlated beliefs, right? Because I mean, I don't know what it means players have to play independently. Let me go back for a minute. That what does it mean for players playing independently is comes in the solution concept, right? This is just you can define a game, right? Give me a suggestion. I can think of the game where players are only allowed to use mixed strategies in their sets, right? That's a well-defined game. And so in that game, you can ask what is the set of rationalizable strategies for every player.
So a surviving strategy might be, אסטרטגיה ששורדת יכולה להיות תשובה מידתית לזה שהם כן עושים קורלציה.
כן. Okay. So I'm still using correlated rationalizability, it's just that now it's like a different, RSA is a different game. It's the game where the other players are forced to play in SA.
But the player is not in A, they can choose any strategy.
They can choose any of their original strategies, yes. Okay. So these are definitions. Now it's the definition of the paper. Okay. This is the main novelty, is this implementability concept. So a suggestion, so this is one of these closed product sets of mixed strategies. I'm going to call it A implementable if it satisfies two conditions. One is what I'll call the agreeability property, which says that for every agreeable player, for every belief that that agreeable player can have over the strategies of the other players, assuming that the other players are playing in the suggestion, okay, that agreeable player has some best reply in their suggestion. Okay. So this means that for every agreeable player, if they believe that the other players are playing in the according to the suggestion, no matter what belief this agreeable player has about how they're playing in the suggestion, the agreeable player has something in the suggestion that they're willing to do. So, as long as the agreeable player is willing to buy the fact that everybody else is playing according to the suggestion, the agreeable player will then be willing to say, okay, I'm fine playing in the suggestion, because I have a best reply, right? For whatever belief I have something that I'm willing to do in the suggestion. So that's the agreeability property. The second property is the rationalizability property, which says that for all the players, if you look at the set of rationalizable strategies in the game, where the agreeable players are only taking strategies from the suggestion, that set of rationalizable strategies is included in everybody's suggestions. So this means that as long as every player believes that the agreeable players are only going to play something from the suggestion, then, if I know that we're rational and everybody else is rational, and there's convoluted fashion and so on, then I know that we're going to play in the suggestion, because we're going to play something from this set, which is in our suggestion.
למה חלק?
The second one, I don't understand. R of SA, SA is the suggestion, isn't it?
S is the full suggestion, but yes, particularly also being SA, it's not.
Okay. So RSA is the suggestion after eliminating the dominant strategies. So by definition, it's a subset.
No. So for players SA, sorry, so I should have probably, I don't So if I have, like I have my a set S, if I added like a subscript as a set here, what I'm doing is I'm thinking about it with only things in the set, okay? Right, so here SA is only restricting the people who are in A.
So it's SA is larger than S because whereas outside S they have the entire space.
Well, you could think of it, so SA is really just is not like, if there are 5 players and 2 of them are agreeable, SA only has 2 coordinates, only has like it's a product only of 2 sets. It doesn't tell me, there's no strategies for the players outside A here. If you want.
When I define R of SA, what I really mean is R of the product of SA
and let's say if you want, you can think of it that way. So it's the product of SA and all mixed strategies for all the other players.
R of a set which is larger than X.
Yes. And so that's not obvious that will be in X. Right?
Okay. So it means that even the players who do not agree,
Yes.
their only rational behavior is going to be
As long as they are willing to buy the
As long as the members of A.
right, exactly. As long as the members in A are access all playing X. So so if they the disagreeable players, the only thing that we need them to do is to willing to accept that the agreeable players will play in S. Once they're willing to do that, they're rational account belief and have account belief rationality, so the R condition, rationalizability property, tells us that they will end up playing in S.
הסעיף הראשון אומר ששחקן agreeable מאמין שכולם משחקים לפי המצע, גם ה-disagreeables?
So it says right, so if הראשונה אומרת שאם אני מאמין שכולם משחקים לפי ההמלצה, לא משנה מה האמונה שיש לי לגבי ההמלצה, אני מוכן לשחק בתוך S.
אבל למה שאני חושב שה-disagreeables הולכים לעקוב? בגלל סעיף 2.
בגלל R. It is a fixed point. It's a fixed point. It's not exactly right. There's a little bit of a fixed point thing here, which is if the rationalizable if the disagreeable players believe that the agreeable players are all playing in S, then the disagreeable players will also be willing to play in S because they're rational and complex rationality. And then the agreeable players, if they believe that everybody's going to play in S, they will also play in S, okay? Because they're willing to break ties in favor of the suggestion. You can think of it this way. It's like as long as you believe they all play with S, the agreeable players are willing to break ties in favor of the suggestion. The disagreeable players are not.
אז כל שיווי משקל נש הוא implementable.
If everybody's agreeable.
Really?
Because if people are not agreeable, then suppose nobody.
לא, אבל כולם agreeable.
If everybody in כולם.
אבל בכל שיווי משקל נש, כולם.
No, so the agreeables is just a set that's given to me, right? The agreeable players. So it's a parameter that I'm going to take as given.
Mm-hmm.
So it could come in as it could be that it's equal to the full set of players, and then I'll get Nash equilibrium as being an implementable singleton. But it can also be a larger set. Sorry, it's going to be a smaller set of players.
Smaller set, let's say one player. So one player, so.
Perhaps what you have in mind is that if you give me a singleton suggestion, so a suggestion that's just one strategy profile, where every player has one thing,
Exactly.
then this condition forces it to be a Nash equilibrium. Yes. So it's true.
לא, אני אומר הפוך, אבל כל נש אקוויליבריום הוא implementable, לא משנה מה זה A.
No. So that's not true. תחשוב, נניח ש-A הוא ריק. Suppose A is empty.
לבד מ-A.
But no, but even if it's easy to find games where A being, so suppose that we all play a game, not with you, and you just want to match me, okay? And you're the only agreeable player, okay? Then it's not, then the set you know, then the way you'd want to think whether something's implementable in that game is you can say, okay, you for any belief you have over what we're going to do.
לא, אבל נניח שההצעה כוללת רק שיווי משקל נש, אז אני יודע.
But we're only restricting you. So good. So it's this part that will make it concrete. Because in that case, we're looking at the game, the restricted game, which you're restricted to the strategy, the suggestion, but we are not. Right? So in that game, we are all have to be playing. We are going. The suggestion has to include all rationalizable strategies for us in that game. Okay. So now we don't care about you, so that's just a set of rationalizable strategies for us in the original game.
זאת אומרת, לא ידעתי שבמחיקת אסטרטגיות אפשר למחוק גם שיווי משקל.
It's not that I'm deleting. זה לא שאני מוחק, זה שאני...
לא, במחיקת אסטרטגיות, לא כל שיווי משקל נמצא בסט של rationalizability.
הוא נמצא, אבל הבעיה היא שיש את כולם. Let's just take a game where, like, suppose if everybody's disagreeable, right? So now I'm going to have to go overcome. I'm going to go some easy examples. So one easy example is that the grand set, the set of all mixed strategies, is always A implementable for any A that you give me, just because it's really saying nothing, right? It's like, well, this thing just becomes all rationalizable strategies are in the set, which they are. And this one says, well, whatever belief you have best reply. Well, of course, right? So that's kind of silly, but it highlights, one thing it highlights is that this thing is an inclusion, okay? And, you know, we want that rather than another thing you could have been added, which would have been an equality. Now, we want it to be an inclusion because what we want it to be is that when you make a suggestion, you're sure that you're in the suggestion. Okay. So that seems like, well, if one suggestion is implementable, if I kind of set a superset of it, it should still be fine. But it's also for analytical convenience. There's going to be a place when I'm doing this theorem about supermodular games where it's much nicer to think about these kinds of definition.
As opposed to what?
You could have had an equality here. You could have required the set of the suggestion that I make to everybody to be the set of rationalizable strategies in the game where the agreeable players follow the suggestion. But we're making it just a superset. So, okay. The set of all rationalizable strategies is also always implementable no matter what A is, because it's the largest best reply set, right? So anything in there is the best reply to some belief against everything else, and if every belief against everything else has some best reply. If nobody's agreeable, then the only way something can be implementable is if it includes all rationalizable strategies. That's just because the agreeability property doesn't matter, and then the rationalizability property, you know, there's no restriction on the other players, so it just says include all rationalizable strategies. If everybody's agreeable, let me ignore the first bullet point for a minute. Okay. The second bullet point relates to the thing we talked about before. When everybody's agreeable, you can implement a singleton set if and only if it's a Nash equilibrium. And you know, you can think of it this way: if I have a singleton and it's a Nash equilibrium, then you know everybody has the best reply to that. There's only one belief I need to consider, right? Which is I just believe you're all playing that, but I have a best reply to it in my set, right? Which is the thing you tell me to do. So it'll satisfy this condition. And the second condition is kind of silly because all it's saying is that we're restricting everybody in the game to just be playing that singleton. So when everybody's agreeable, so then it's just the singleton is itself.
When you write SI,
Yes.
But SI itself is a set of mixed strategies?
The set, so let's see. So mixed strategies. And so, if
But
everybody's,
if you take a correlate, in your examples you said that every Nash equilibrium is
if everybody's agreeable, then a singleton profile, one profile, is implementable if and only if it's a Nash equilibrium.
oh, because the suggestion must be a product.
Because, so what does it mean for me to have a singleton thing, right? It's like, it's just one, one strategy for every player. And so then, the only belief that I need to consider is, well, I just believe you're taking this strategy. Right? Because this thing is just a singleton. And the set of distributions over singleton is just a singleton. Meaning? Hope I'm making sense.
So S minus I.
In that case, in that example, we can,
I'm again confused.
I have a board, so I
the
can use it.
suggestion, no, but what confuses me is that mixed strategies
But it's not,
use.
it's not that
So
important.
SI denotes the set of
You don't
new
know how to do it.
strategies, but the suggestion is a subset of
Okay, let's,
strategies.
we can do it this way, why not? I already spent, let's get into it. So,
This is what
This-
I was
we're using xi for players' pure strategies. S bar I is the set of all mixed strategies. Si is some subset of that. A suggestion is some product set of mixed strategies. Okay? So we're all good? So now there's the question of what does it mean a suggestion is a singleton, right? That's just the product of the singleton sets. Sorry, that should do. Okay? Are we good with that?
but S
And
minus
now-
I, now I want to see what is delta of S minus I.
Good. So delta of S minus I, right? In this case is delta over the set, this strategy where, right, so which is really just the set of all distributions that put a probability 1 on that profile.
Yes, so you identify this Dirac measure.
So there's a Dirac measure over, yes, and right. Right, so then there's only one belief I need to worry about, which is everybody's following this exact singleton. And I must have a best reply in my suggestion, which is just my singleton that you told me to do.
Yeah, but in general I don't understand what this object is, because mu minus I is a distribution over
Products.
profiles of mixed strategies.
True. So perhaps this is the little thing that I said earlier that might have been, is this going to help you? I don't know if that's hopefully not. Right? So wait, so this is, let me say, you're right. This is a distribution over mixed strategies. So it's a distribution over distributions. Okay? But,
What does it mean to be a best reply?
good. So that is this thing. So I'm going to, when I'm sticking distributions into my functions, I'm going to think of it as doing expectations. So if I wrote, suppose I only have 2 players, give me that for a minute. If I write ui of sigma 2, really what I want you to do is to take expectation, or u1 of sigma 1. Like that, okay? So if you give me sigma 2 as an input into u1, I want to take expectations. Now, you might ask, what do you do if you give me a distribution over distributions? Take down expectations again. Okay? So I'm just extending everything linearly so that I don't have to think too hard exactly about those things. But this is, I'm not inventing this particular way of doing it. It's like common when we do. Okay. So now we're good?
Yeah, I believe you that it works.
Good. At least you're willing to. At least they converted you to an agreeable audience member. At least for now. that's this thing. Hopefully we're all on the same page. Here, I just want to highlight that the definition, this agreeability property that I gave, is basically borrowed from that preparation set literature. It's not exactly what they do because they restrict attention to product beliefs, we're allowing correlated beliefs, but it's similar to how we're using correlated rationalizability versus like, independent rationalizability. If you want after the talk, I'm happy to tell you more about prep sets. They're kind of fun. Okay. And they're the inspiration for this particular part of the definition.
So that's a good thing? יש לך עכשיו קשר עם ספרות אחרת? או שזה לא טוב, כי זה כבר עשו מה שעשיתם?
I mean, I don't know. I think nobody has done this kind of way of mixing things together. I don't think it's a problem or, it's a relationship to the literature, and we give them credit that, the idea is taken from there, this particular way of defining, thinking of things, but they're considering, in that literature, they're considering an alternative solution concept to mixed strategy Nash equilibrium. So the idea there is mixing is a weird thing maybe for people to do. I don't know, I'm just giving kind of what I think is the premise. The way I read the premise of this literature, they think mixing is a weird thing for people to do. Instead of having beliefs in some sense about mixing, how about think about like beliefs over a set or something. So I know you're going to do a set of strategies on what in the set, and then what can be justified in some sense as something that looks like an equilibrium. And they define spreads like Warnerville is the first, and Warnerville after sure is the second.
זאת אומרת, ככל ש-A יותר גדול, ככה S יכול להיות יותר קטן.
כמעט.
In general.
It's almost right. The thing is that works if this was exact inequality. With the subset thing, you could get a thing where, like, combined with A, where there's some strategies that would be eliminated with iterated deletion, but I'm forcing my agreeable players to have a best reply to them. So and then if I switch an agreeable player, I make a disagreeable player to an agreeable player, that will require me suddenly to have other best replies to some beliefs that I didn't have before. Okay. So that creates a little bit of a tension. But because we're going to take worst case, which is what this next thing is going to do, that issue doesn't matter for the optimal suggestion. So I told you what is our implementation concept, which is this implementable thing, A implementable, or agreeable, we like to call it agreeable implementation. But I haven't told you how the principle evaluates these sets, because it's a set, so you have to say something about it. We don't have this thing. One, we're going to take worst case approach. So for any, you can implement some set. Script SA is the set of all A implementable suggestions. And so if you give me an implementable suggestion, our principal is going to take the worst case among them. Okay? Taking that sort of conservative approach.
פספסתי אולי, איך אתה חושב על הקבוצה A? אתה אומר שזה נקבע אקסוגני.
כן.
So,
we're going to think
what is the idea behind it?
So it depends on the setting and what it is. So let's say in an organizational setting, you can think of these are the people who are kind of close to the CEO. The CEO would be the principal.
זה יותר מיישרים קו עם
כן.
יש להם איזושהי מוטיבציה
כן. They're kind of willing to go along with it, but they're still selfish, right? So they're still going to do it only if it's in their best interest.
כן.
אבל מה באמת סטינג שיש לך בראש כדוגמה לזה, שיש שחקנים כאלה ושחקנים כאלה?
So I don't know if I guess you're in Israel, you follow politics all the time. The people who you'd call maybe Netanyahu's lackeys, who will do whatever principle what he says. Of course, they're not going to do anything that he says if it's not in their best interest. But as long as it's in their best interest, they're going to follow along. Then there are the people who are not. Yair Lapid might not.
רל"בים. רק לא ביבי, רל"בים.
Okay. So, but they're still rational, so they're still going to do, if it's, given what they expect the other players to do, they're still going to do something rational.
Makes sense.
As an example, or your regulator, let's say you have like bank runs, and trying to run bank runs or something. Some banks you can kind of talk to and that you're sort of close to the government, the big ones. But then there are a bunch of small ones that you don't talk to them, and then they need to coordinate stuff like that.
But here you kind of talk to everyone, like it's like.
Yeah, you're saying things to everybody,
But they don't listen to you?
it's enough. Really, what you really need is that everybody sees what you tell the agreeable players. That's what's important, right? Because disagreeable players, really, they can kind of infer their part, what they're supposed to be doing from this part if necessary. But
so it would be equivalent if you also only have a public signal only to the agreeable platform.
as long as the disagreeable players need to be able to see it, but you don't need to tell them what to do.
ממש equivalent? זה לא היה משנה?
There's some definitions of implementability that I'll tell you that you would have. It would not matter for the principal's value, and it won't matter. Let's say there are some implementable sets that you won't be able to do in some sense because you're kind of restricting them in ways that doesn't matter, but it's not. Okay, so let me give you just a result that says roughly kind of, but so I said it's not exactly what you said, but it kind of behaves the way you would expect. Okay? So if nobody's agreeable, the only thing that's optimal, like the optimal thing, it's not the only thing that's optimal, but the optimal thing to do is just suggest the rationalizable strategies. That's because it has to be a subset of anything that's implementable, so you might as well use the smallest one you can. You're taking worst case. If everybody's agreeable, it's optimal to implement your best Nash. The proof for that is give me an implementable set. You can think of the game where players have to play things in an implementable set. Okay? That game has a Nash equilibrium. The implementability property tells me that Nash equilibrium will also be a Nash equilibrium of the original game after you reduce compound lotteries. And that means that this Nash equilibrium is weakly better than the worst thing the principal could get from that game. And so the principal might as well just implement this Nash equilibrium. So you just implement it. So anything you can implement is worse than some Nash equilibrium, and you know the best Nash equilibrium is implementable, so that's going to be better than anything else. And then finally, the monotonicity you'd expect, if you have more agreeable players, in a superset sense, you have a higher value.
Is it a general thing that the supermoon would affect the maximum?
No. That's why I wrote this as a supermoon. No, because it's the same problem with when you're doing implementability with rationalizable strategies, any kind of design, you get an openness problem where it's possible that something is unique best reply for anything in the sequence, but then in the limit the best replies explode or the unique rationalizable thing explode, like the rationalizable set explodes. Right? Basically, best replies are upper hemi-continuous, middle lower. So that creates a problem here. That it could be that I have a sequence that converges to the best, that picks the minimum and makes it converge to the best thing, but then in the limit suddenly things explode. Okay? You can mimic the effect of bonuses with a player. It's not so it's not in general true. It is true in these two cases that you can say what it is, that there is one. So I have some kind of simple example with matching pennies that highlights why you have to have a set value definition, in the sense that if you don't have a set value definition, if you require the same definition I gave you but with quite singleton sets, you might not be able to get it. So I said that you had to have 75 minutes, having a 12:30. Is that right?
12:30.
Okay, so I think maybe I'll skip this, since we already talked about the definition a lot, but I'm happy to go over it if people are very curious.
You can do it.
Huh? No? So let's skip? Huh?
Okay, up to you.
Up to you.
You want to go over it? So this will just highlight, so suppose you have like two players who are playing matching pennies, right? One of them is agreeable, the other is not. If you try to implement a singleton set, so just a singleton strategy for every player, you cannot do that here. And to think about it, suppose you're trying to implement, tell our agreeable player some mixed strategies. That's one mixed strategy. Now let's think about the other player. Okay? Right? Suppose that mixed strategy was a pure strategy. Well, then the only thing rationalizable for the other player in the game where they know that you're playing that is the other thing. So if you're telling me heads, they'll want the tails. But then, of course, heads is not a best reply to that. Okay? Now, this argument also works for mixed strategies, right? Because for any mixed strategy that you give me, there's some pure strategy for the other player that's rationalizable, and then, of course, my only best reply to that is the pure strategy that matches it. So the only way in this game, even though you have one agreeable player, to have something that's implementable is to just include all pure strategies in your suggestion. Okay. Make sense?
Mhm. Yes.
Okay. That. Now you can ask. Sorry. Yes.
To understand, the set of all pure strategies is always
Yes.
a suggestion.
It's always implementable suggestion. Yes. Well, okay, no, let me pause for a minute. Not really the way I've defined it, but you wouldn't have seen it from the web. So I've written rationalizable strategies. When I said that, I meant all...
Mean over all the rationalizability.
I meant all mixed rationalizable strategies. And so in that sense, it's not always implementable because you don't include the mixtures, but it
But this
doesn't
for
matter.
active players, I can
It's
suggest all the pure
I
strategies.
think, yeah. So I
For
think,
the agreeable players.
yeah, the agreeable players you can always implement and give them all the pure. But I don't think it matters for any of the things that I've done. So I think you could have defined. I'm not 100% sure, so don't blame me. There's a chance I'm wrong, but I think could have defined that rationalizability property with like all pure strategies, and it would have been the same results. Yeah. So then the answer would be yes. Yes.
הדבר היחיד שאתם בוחנים זה איך זה עובד ביחס לפריים, לאובג'קטיב?
Well, we can tell you what is the best implementable set in supermodular games.
The best,
The best
object.
Kind of objective, yeah, the
Yeah.
worst case objective.
לא, אני אומר, האם יש לכם דברים אחרים שאתם מנתחים, או שאתם אומרים, יש פונקציה פאי, שזה האובג'קטיב, ועם זה אני עובד.
כן, אז יש לנו פונקציה...
מונוטוניות אמרת שזה לא בדיוק.
אז נכון, אז יש לנו תוצאה על מונוטוניות שקשורה, אם הופכים את ההגדרה פה לשווי, אז מקבלים מונוטוניות של ה-implementable sets ולא של ה-objective, אבל כן, כל מה שאנחנו נעשה פה זה חושבים על ה-objective כנתון ומה אני יכול לעשות מ-objective. כמובן שאתה יכול לעזור בין זה לבין, אם אתה נותן לי objective שנניח אתה רוצה לדעת איזה פונקציות, social choice functions are implementable in the sense, you could define an objective that tells you one when you're in the set, when you implement the function and zero otherwise, and then you can ask when is my value here 1, and then you can use the results for that. So that's example number 1. It tells you can't always implement a singleton. Then you can pretty easily extend this example to say that even when you can implement a singleton, you don't always want to. Okay? So suppose that I took our matching pennies and I allowed players to choose to be out. Okay? And if they both choose to be out, then they get both 1. And suppose now our principal wants to maximize the sum of their payoffs, right? And of course, I put the numbers so that if you implement something in this square, then you're going to get a value of 3. If you implement out, which is a Nash equilibrium, you're going to get a value of 2. Out is to out. The rationalizable thing for you to do is just play out, the only rationalizable thing. And therefore, the same thing from the agreeable player side, so that's implementable. But another thing that it's implementable is just this corner, so all mixed strategies over heads, tails, and heads, tails, and that will give you a higher payoff, give you, as a principle, give you 3 rather than 2 you get from the end. Okay. So next thing we have a general result about supermodular games. So these are the definition of supermodularity here is the usual one from William Roberts. The only thing that's maybe the only things that are slightly different is that we're going to require our relation to be continuous. Then instead of doing that, they impose some order continuity.
יותר לאט בבקשה, אני לא זוכר מה זה.
Okay, so supermodular games, sorry, yeah, no, of course. So supermodular games are games where every player's pure strategy set is a complete lattice. Okay, so every set has a supermode and an infimode, according to the order you give me. We're going to require the ordering to be continuous. So let's say if I have 2 sequences that have the yn and xn, yn is always better than xn. The limit y is better. The limit of y is better than the limit of x. The utility functions are supermodular in the order. So like the u of the sup plus the u of the inf is larger than the sum of the u's from those 2 different things. And it has increasing differences in my strategy and the other strategies. That means that if you look at the difference, fix the other player strategies, and look at the difference for me between my utility with a high action and utility with a low action. That difference now increases as I increase the other player's strategies. That's what increasing differences says.
Does it imply that the U itself is monotonic in action?
No, it doesn't have to be monotonic in action. No. So a simple example is quadratic loss with 2 players playing quadratic loss. Where I want to, we both choose a number between 0 and 1, and I want to match your number, and you want to match my number, and our utilities are, negative of the quadratic difference between the 2. That will satisfy these conditions, and that will be an example that I'll use. Well, see if I can do it. I think I will. So I'm going to give you a theorem about these kind of settings. The one thing that I'll also assume that the principle's objective is that it's increasing in the order. So you kind of want people to take higher things. Examples of such settings are any kind of like coordination game or like beauty contests, all these things, those kind of things tend to work like this. Right. These represent games where like I really care of trying to match kind of the other players, roughly speaking. Like I want to do higher actions if other players are doing higher actions, but if other players are doing low actions, I want to do low actions. So going to 2 definitions for a strategy profile X. Let S superscript X be the product set of mixed strategies where every player is only going to use pure strategies that are above their part of the X. So if our strategy sets are intervals, and I give you, let's say, just like the X is just 0.1 for everybody, then S of that profile is we're going to take an action that's larger than 0.1 with probability 1. Gamma, so that's S of X. Gamma of X takes a profile and returns a profile. The agreeable player's part of the profile is the highest Nash equilibrium for them in the game where the disagreeable players are following, like are fixed to their part of the incoming profile. And for the disagreeable players, it's kind of the opposite. They're thinking, let's take a look at the game where the agreeable players are fixed to what I told them in the profile to do. The disagreeable players are going to play the lowest Nash equilibrium.
Let me see the thing. So you fix the actions of the, let's say the first step.
Yeah.
You fix the actions of the disagreeable players.
Yes.
And now you have a game where the players are only the
Agreeable players.
And in that game, you look at the Nash equilibrium with the highest.
Yeah. Yes.
כל אחד בנפרד, אני לא מבין.
When
No.
you write this line, it means that the high of this Nash equilibrium is maximum.
It's high. Well, because the game is supermodular, that game has a highest Nash equilibrium. You can show that. It's not obvious, but there's one that is highest according to the order, even if the order is there's one that's according to the order.
If you take the
Super.
super, I don't know
Or
what
it-
you call it, the supermodular over the Nash equilibrium, it is going to be Nash equilibrium.
Yes. Yeah.
How do the disagreeable players influence things?
So you fix what they're doing.
Right.
So you fix what they're doing, and now that defines a game between the agreeable players. It has a bunch of Nash equilibrium. That game is also a supermodular game. And so you can look at that Nash equilibrium, and there is going to be a highest Nash equilibrium in that game.
For all? לכל השחקנים
Yeah, it's going to be the highest one for all the
לכל
agreeable.
אחד בנפרד.
Okay, it's so it's a Nash equilibrium, and so there are the best thing, but it's also there's no Nash equilibrium in which any, let's fix a supermodular game. So going back, fix a supermodular game. There is a Nash equilibrium in which in every other Nash equilibrium, all players are taking a lower action. Okay?
Is it true that that in a supermodular game, the set of Nash equilibria is a lattice?
Yes.
It's a complete lattice.
It's a complete lattice. That's not an easy result, but that is true.
Now, in this setting, if you vary the set of the disagreeable players, you also vary the Nash equilibrium, I presume, because you've got a different game each time.
And this part.
Yeah, vary
Yes.
the disagreeable.
Once you fix
that, I understand. You
Yeah.
got some Nash equilibrium. Now, vary the disagreeable, the set of disagreeables,
Yeah.
you might have different Nash equilibria emerging.
I mean, in the restricted game, right?
Yeah.
Yeah, that's true. Yeah, that's why I subscripted this by A. Right?
So then you can ask, what is the highest payoff over all the possible disagreeables?
Well, this is taking the disagreeable set as fixed.
I know, I'm saying, suppose you varied it. you
Well,
got
that will
some-
always be the highest Nash equilibrium in the full game, I mean, across all sets. Because that's when,
So it doesn't give you anything.
no, yeah. So that's
All
right.
right.
So the theorem that we have says that if you have a supermodular setting, what you do is you find the highest fixed point of this function, which there is one. So there's a highest fixed point in the order. And the best thing for you to implement is something that tells all other players, please take either the action that is this highest fixed point or something higher.
So this gamma is a monotonic function.
Yes. It's not, that's the Milgram-Roberts or Monta static style thing. Yeah. It's not, if you're not, if you don't read Milgram-Roberts before going to bed every day, you might not remember that. But yes, that's like a fact of these kind of these supermodular games is that the best reply, supermodularity that gives you with single crossing, with this increasing differences, gives you the best replies are increasing. It also gives you the Nash equilibrium increasing. In fact, it also gives you that the highest Nash equilibrium is the highest rationalizable action for everybody, and the lowest Nash equilibrium is the lowest rationalizable action for everybody. These are games that are super nice. If you don't, I highly recommend reading Milgram-Roberts if it doesn't, but if you haven't, and if you have read it and you don't remember, I highly recommend going back to it. It's just one of my favorite papers. Yeah. Okay. So the theorem is basically telling you you want the highest fixed point of this.
So it's not clear that it's well defined, right?
What?
It's not clear that there are fixed points and that the fixed point can be sorted and there is a maximum.
So
still need to know that
good.
well
So
defined.
if all you knew was the definitions that I've given you, you're absolutely right that it's not obvious that this fixed point is well defined and so on.
And the loudest
But
fixed point.
yeah, okay. So, but how can we get that? There is Tarski's fixed point theorem, which takes monotone functions and gives you over a complete lattice and gives you fixed points, tells you there exists a fixed point, and it actually tells you that the set of fixed points is a lattice. Okay. And then what you do is you use the results from Roberts to say, oh, these things are monotone in whatever you plug in, and so this gamma is monotone, and therefore it has fixed points. Their fixed points are a lattice, so there is a largest point.
That's like a standard thing to do.
Well, if you're playing with supermodular games,
That's what I'm asking.
then yes.
Supermodular.
In supermodular games like Milgram Roberts, they establish existence, right? So I said like, oh, they don't use continuous orders without use some order continuity properties that they use. Those order continuity properties are like fancier and different than the usual continuity properties you're used to, but that's because they can get existence from the Tarski fixed point rather than from like our usual kind of like Kapitani style results. And so they yeah. So I had like a diagrammatic explanation of the proof, but maybe I'll skip it and I'll just give you an overview of these applications. I think I am probably out of time.
You're not out of time. You got 6 minutes.
I had 6 more minutes. Yeah. So, but let me. I still think the proof is not the optimal thing to do. I think I'll do the network games because that might also help connect to the application to the definition of this. So we have all kinds of different applications. One which I think is very nice is uncertain availability, but I'm going to get back to talking about it later for lunch. Let me talk about the network games. Okay? So this is a very special class of games. It shows up in a lot of places. Things that look like it. In this games, every player's action set is just the interval 0, 1. We have one of our increasing profit or principal objective functions, pi. Give me kind of a matrix, positive value matrix for the players. Okay, so Gij, so I have for every I and j, I have some coefficient for the I and j. And player i's payoff from the profile x is there's some nuisance term that depends only on the other player's actions. And the thing that matters for player I is their action times the product of the vector of other players' actions with the I row of the G matrix, alternatively the sum of the other players' actions times the corresponding coefficient. 1 minus, of course, some kind of like an effort cost. You can think of it, maybe I'm engaging in there's like a social network, and Gij tells me how good of a friend or how much I care about seeing the feeds of other, the posts of some other people, and Xj is how much like people post. Okay. So if I have a lot of friends on the network, or people that I post things that I like, then I want to be there. But of course, being there and posting there is costly. So say that our network is undirected if whatever player I cares about what player J does, player J also cares about what player I does. Okay? So the one special case would be if Gij equals Gji, but if the matrix is symmetric, but you can do also things it's not. So our result says that in this kind of game, the optimal thing to do is to tell for every player, who is in the same component as an agreeable player, so who like cares about somebody, who cares about somebody, who cares about an agreeable player, that player is going to play the best Nash equilibrium, the highest Nash equilibrium in this game. All other players are going to play 0. So you can think of this kind of graphically. Okay, so these two players here are linked if they, the coefficient between them is positive. Okay. And give me one of these G's that creates, you have all these like different connected components. And what our proposition says is that anybody who has no agreeable player in the connected component is going to just do their lowest Nash equilibrium. Everybody who has at least one agreeable player, these are like smiley faces, in their connected component is taking their highest Nash equilibrium action. Okay? So
there is kind of discontinuity. If JZ is positive but extremely small, it completely changes what you can achieve.
Yep. Yeah. Exactly. These kind of games have like a, just give me, a person, connect a person a tiny bit to an agreeable player and I can lift them up.
So again, can you go back to the result? Proposition 3.
That's because of your property R, right?
I mean, I don't know, it's the definition
Yeah, but
of a game. It's
that's the fact that you can
once I
people
know-
that are disagreeable to be agreeable, given that they know that
it's because they know that the agreeable players are going to do something good, and the agreeable players are willing to do something good because they. So I have a more specific example if you want. So I can maybe
I
that.
want to consider the case that the network is connected.
It's fully connected? Then having one, which is this will be an example like that. Okay? So having one agreeable player will be enough to get you the highest action that you can achieve. So let's look at this example maybe.
That's from the connectivity alone?
What?
That's from the connectivity alone?
Yeah.
You get the highest Nash equilibrium.
Yeah, you can implement the highest Nash equilibrium, which is, in this world, the principal best Nash equilibrium.
And the way to implement it, you just suggest to the agreeable player whose direction.
Well, I think for them what you end up doing, what you have, yes, in that case actually it is, yeah. You just tell them take that, the highest Nash equilibrium, and actually you can tell that to everybody in this case. More generally, you sometimes need in supermodular, if you have this connected component, you can really just specifically implement the best Nash equilibrium. I can walk over this example if you want, if you're willing to give me 5 more minutes. So this is an example that kind of has that structure at the top. So we have 3 players. Player 1 is agreeable, 2 and 3 are disagreeable, and player 1 cares about what player 2 does, player 2 cares about 1 and 3 cares only about player 2. Specifically, player 1 wants to match what player 2's action is. Player 3 wants to match player 2's action, and player 2 wants to match the average of player 1 and player 3's action. Okay? So let's see what how our theorem from before plays around in this example, and then how it gives us the best Nash equilibrium here. Which, by the way, it's clear the best Nash equilibrium here for you as a principle is everybody plays action 1, right? So let's see how we can get that. So let's start with player 1 is our agreeable player. The highest Nash equilibrium fixing whatever other players are doing. This is one player, so it's just the highest best reply for that player, given what the other players are doing. Well, whatever that is if I know what player 2 is doing as player 1, I have only one best reply, just match. Okay. Now let's go with players 2 and player 3, right? Them, they're disagreeable, so we need their lowest Nash equilibrium given what the agreeable players are doing. So the lowest Nash equilibrium given what player 1 is doing. That turns out to be both matching player 1's action. To get yourself there, think about iterating, even elimination of like strictly dominated strategies kind of from the bottom. So like suppose player 2 and 3 like think that they're going to do 0, and you've told me what player 1 is doing. They're just fixed at x1, right? So if player 2 and 3 think that player 1 is that each other are doing 0, what is player 2's best reply to that? Well, you take 1/2 x1, right? x3 is still doing 0, but now once player 3 thinks that player 2 is taking 1/2 x1, player 3 will take 1/2 x1. But now player 2 will want to take 3/4 x1 because they're taking the mixture of the average of x1 and 1/2 x1, which then gives you that player in the next iteration, you know that player 3 will never do anything below 3/4 of x1, which now you can keep going, right? You can see how we're going to end up converging that into x1. So that's their lowest thing that they can do. Therefore, the gamma function that I gave you before, you give me a full strategy profile, and for player 1 it returns x2, and for player 2 and 3 it gives you x1. And so the only fixed point that these things can, that this function can have is give me anything where they're all taking the same action. That will be a Nash equilibrium, it's easy to see. But now, in particular, the highest thing I can get is this, just everybody taking 1. Okay. So that's how that works. Now, we also have a version of this example where we now make only player 1, player 2 influence player 1, but player 1 not influence player 2. So player 2 and 3 want to match each other. Okay? So 2 no longer cares about player 1. And you can ask what happens here. So this is the undirected case, right? So in the proposition I gave, I have this is the directed case. The proposition I gave, I have undirected. This is now a directed network. So player 1's world is still the same. So we still get x2 for there. But now, when we're doing the lowest Nash equilibrium between 2 and 3, given what x1 is doing, player 1 is doing, they don't care about player 1. So the lowest Nash equilibrium for them is both of them taking 0, right? So now our gamma function becomes x2, 0, 0. The only fixed point you can get is everybody taking 0. So in this, once you make the network non-directed, you lose that kind of like instant or discontinuous infectiousness. So I'll stop here.
רק עכשיו אני מבין, ה-lowest Nash equilibrium זה מהפרספקטיב של המתכנן.
אז זה lowest ב-payoff, the lowest מבחינת ordering, the orders of the
לא,
actions.
הם מקבלים
it's
בכל
not
מקרה.
lowest payoffs, it's lowest in the order. So here we have an actual order, the actions are in the unit interval. So
אבל ה-lowest בהגדרה זה ב-lowest...
It's according to the, not payoffs, it's order. It's order, but it also matters to payoff because it made the principal's objective increasing in the order. So for the principal's objective it's the same, but for the players, no. The players can get highest payoff.
כן, זה אותו דבר.
Yeah. So I think I'm way out of time, so I don't have all these like fun things, other fun graphs to show you, and the winter model to show you, and so on. But hopefully, we understood what we were trying to do, remember the definition. And if you're thinking of doing any kind of implementation, or you want to think maybe I want to bridge between best and worst cases, you might consider this agreeability property.